Hello everyone, I'm Matteo Galli, a PhD student in APC laboratory in Paris, and today I will present an overview of the Deep Underground Neutrino Experiment, focusing on its design, experimental strategy, and physics goals. With this ambitious project, we want to address some of the most fundamental questions about neutrinos. The experimental discovery of neutrino oscillations in the end of the 20th century has the consequence that the flavor energy states are a mixture of the mass energy states connected through the PMNS matrix. So the masses of neutrinos are not zero and differ from each other. If we make the assumption that the PMNS matrix is unitary and 3 by 3, we can parameterize it in this way. And it depends by three mixing angles, which give the amplitude of the oscillation, a single CP violation phase, and two independent mass square differences, which give the frequency of oscillation. So with this assumption, we have 6 parameters describing oscillations that we can measure. Over the past 2 decades, experiments have measured most of these parameters with good precision, and the open question for the next generation detectors are about the correct mass ordering, normal with the M3 greater than M2, or inverted with the M3 smaller than M1, and the violation of the charge parity symmetry in the electronic sector, measuring the delta CP values. But these questions are only part of the neutrino picture. In fact, these measurements are needed to understand whether the model is correct. And if it's not, what are we missing? Are there some other neutrino species? DUNE is designed to definitely answer this question through precision measurements of nu mu, nu e, and anti-nu mu, anti-nu e oscillation. DUNE is a long baseline experiment located between Fermilab and Sanford Underground Research Facility in South Dakota, and it consists of 3 parts. Fermilab will provide a 1.2 megawatt wideband neutrino beam. The beam energy spectrum spans from 0.1 to 10 GeV, covering both the first and the second oscillation peaks. Also located at Fermilab is the near detector complex to characterize the unoscillated flux and neutrino argon cross-section. The beam will travel through the Earth for 1,300 kilometers to the far detector located at 1.5 kilometers underground at the SURF laboratory. There, the far detector complex observed the oscillated spectra with high precision. This long baseline and H-matter effect making DUNE uniquely sensitivity to the mass ordering. DUNE will be built in 2 phases. Phase 1 will include 2 far detector modules and the initial 1.2 megawatt beam. Phase 2 will upgrade the beam beyond 2 megawatts and add more modules for far detector and one for the near detector, increasing sensitivity and statistics. Speaking about the near detector, it includes 3 complementary subsystems. The first one is a 50-ton liquid argon TPC with pixelated charge readout that matching FD technology, and a prototype called a 2x2 has been built for this detector and recently tested at Fermilab with almost 5 days of beam and currently collecting data from calibration. Then there will be TMS, a magnetized mu spectrometer for charge and momentum measurements, and SAND, an on-axis magnetized tracker and calorimeter for flux monitoring. The first 2 modules allow the prism technique, where the near detector moves off-axis to sample different neutrino energy spectra, and a linear combination of data will be used to reproduce the oscillated neutrino spectrum at the far detector. During the phase 2, the TMS detector will be replaced with a system based on argon gas. For the far detector, it will use liquid argon time projection tumbler technology, which combines excellent spatial resolution with the energy reconstruction, and this allows full 3D event imaging with a good energy resolution, particle identification, and topological classification of the events. In this moment, 2 detector designs are being realized. The horizontal drift on the left with an horizontal electric field 4 drift regions and wire planes for the charge detection, and a vertical drift with a vertical electric field, 2 drift regions, and using printed circuit board charge readouts for longer drift distances and improve the signal to noise. These technologies have been successfully validated through the Proto-DUNE program at CERN, which demonstrate full-scale modules and achieve excellent agreement with the simulation. The HD technology was tested for the first time in 2018 and again during 2024 with beam and in calibration mode. Vertical drift was tested most recently last summer and is currently collecting data without a beam. This is a list of the main physics goals of DUNE, but today we will focus only one part, giving priority to the highlighted points. DUNE will measure the nu mu, nu e, and anti-nu mu, anti-nu e oscillation, and mass orderings and delta CP values have a different impact on the two oscillation channels with opposite effects and different energy dependencies, as you can see from this distribution, where the most contribution comes from normal ordering with delta CP minus pi over 2 for nu e in red, and from inverted ordering with delta CP plus pi over 2 for the anti-nu e. Thanks to the very long baseline, matter effects induce an asymmetry between neutrino and anti-neutrino appearance probabilities that depend directly on the mass ordering. And DUNE, by observing this increase or decrease, will be able to determine the correct order. Here we can see how spectral information can be used to show sensitivity to mass ordering and delta CP. As can be seen, there is no degeneration in the parameters, the ellipses are well separated, and the delta CP values do not overlap. But if we consider the information provided by the shape of the spectrum, we could do even more. For example, at the low energy, we obtain greater sensitivity to delta CP values with a non-flat ellipses. And if we take in account the peak of the energy spectrum, we obtain the greatest separation between the two mass orderings. Then, if we look at the high energies, we obtain circular ellipses in which the delta CP degeneracy has completely disappeared. So considering this power derived from the uniqueness of DUNE baseline, we can determine the sensitivity to the mass ordering, and in the base scenario, DUNE can determine the mass ordering at 5 sigma in 1 year of running. And even in the worst case, it will be possible to reach 5 sigma in 5 years. So DUNE will definitely determine the correct mass ordering of neutrinos. Regarding CP symmetry, DUNE is expected to provide the best resolution of delta CP with a precision of 10-15 degrees, especially if CP is conserved. And as we have seen, it has the ability to resolve the degeneration between different values thanks to the large distance and energy. Moving now on DUNE's capability beyond the beam. Speaking about atmospheric neutrinos, we know that cosmic rays provide a constant flux of multiple flavor neutrino and antineutrino with a wide energy range up to several TeV. And these neutrinos arrive from all zenith angle and pass through various layers of matter. Moreover, we know that before the beam, the first two far detector modules will be in operation for 2 years, where the main source will be atmospheric neutrinos. And we will expect 2,000 atmospheric neutrino events per module per year with a few tau neutrinos. So this provides sensitivity complementary to the beam. At low energy, we have a fast oscillation below 1 GeV for outgoing neutrinos. As you can see in this plot, energy versus the cosine of the zenith angle, the direction of the neutrinos. The ability to reconstruct sub-GeV atmospheric events increases the sensitivity to delta CP measurement in a complementary way to the beam. At higher energy, between 2 and 10 GeV, we have an effect due to the mass ordering. Sensitivity increase if we are able to distinguish neutrino events from antineutrino events, And since there is no magnetic field, this is possible in DUNE by tagging Michel electron events. The possibility of making this distinction in DUNE is currently part of my work on atmospheric neutrinos, so I will spend a couple of slides on this topic. The idea is to find a way to target the muon charge using Michel electrons, and we aim to discriminate the charge by observing the decay events. We know that muon decay produce an electron called Michel electrons, and in liquid argon TPC, for stopping muons, the positive muon always decays, while the negative muon decays 28% of the time, and the 72% is captured by argon nuclei. So our goal is to optimize the selection efficiency of Michel electron tagging to separate the new mu sample. And to do this, the strategy is to search for Michel electrons hits around the endpoint of the reconstructed muon track, as you can see in this event display. So for the moment, the selection is based on hits taking into account positions and number of hits close to the endpoint of the muon track. And in this way, I found an efficiency of 0.52 with a purity of 0.9. Now I'm evaluating the impact of this separation on mass ordering sensitivity. And what I can show you today is the probability that inverted ordering could explain data assuming normal ordering parameters as the true parameters. So here you can see the comparison between the no separation of new mu anti-new mu events, the separation with the Michel electrons tagging with my efficiency, Michel electron tagging with a perfect efficiency, and a perfect separation of the new mu and anti-new mu events. What we can appreciate for the moment is just that even considering the efficiency that I found so far, we can see a decrease in the probability that inverted ordering parameters could explain the normal ordering setup. So this study is promising, and I'm working now to include backgrounds in the sensitivity study. At high energies, we can see the effect caused by sterile neutrinos. DUNE can observe the mass parameter delta m square for 1 below 1 EV square. And the challenge lies in the non-containment of very energetic events. DUNE also has a unique sensitivity in the MeV energy region. This ability allows the detection of these two interaction channel, charge current and elastic scattering. And these interactions give the possibility to look at astrophysical neutrino sources. For supernova detection, measuring the complete neutrino flux from a supernova burst gives the possibility to study core collapse mechanism. And DUNE has a good pointing resolution that depends on the supernova location that can be used to do multi-messenger astronomy. Also has a unique sensitivity to the electron neutrino burst from the supernova spectrum. Additionally, DUNE can observe solar neutrinos, testing day and night asymmetries. Studies are ongoing on the background that limits the sensitivity to oscillation parameters. So far, the excavation and the infrastructure at the fire detector is completed. Farside cryostat construction are about to start, and after this, the installation of the fire detector modules. By the end of the 2029, we will be ready to start our physics program with atmospheric, solar, and supernova neutrinos. In summary, DUNE is a next-generation experiment designed to answer fundamental questions, testing the three flavor paradigm of neutrinos. It will deliver definitely measurement of the neutrino mass ordering and will provide a unique resolution of delta Cp values. I gave you also an idea about the large capabilities of this physics program in non-beam physics. Until now, we got a successful detector prototype program with ProtoDune at CERN and 2x2 at Fermilab. Construction of the detector continues. Stay tuned. The first fire detector modules are coming soon. Thank you for your attention.